Real exam questions. This is question 28, dealing with slab design with the method of equal deflection. A warehouse in a factory has a type 2 rectangular floor slab, which means fixed end at one short side and 3 simply supported ends on the other side. This last slab is subjected to a mobile load of 5 kN per square meter characteristic. The floor finishing is not provided. The concrete quality is C2530, and we will consider in this question only a diameter of 20 as reinforcement diameter. What is the required thickness of the slab? And use method of equal deflection. First, we see that in the direction of B, the elastic formula for equal deflection is given by this, and in direction of A, because the deflection in the middle of the span, so it means for a beam at one side simply supported and the other side is fixed, then you have this expression. For equal deflection, the must be the same, the deflection in the direction of B, and must be the same as the deflection in direction of A. And that leads us to, because it's the same stiffness in both directions, to this expression. Or you can express the total load transfer of direction B into the load transfer of direction A. We also know that the total load is equal to this in direction A plus the one in direction B. And together with those two formulas, we find that QA from this is equal to the total load divided by this coefficient. Now you remark immediately, this is in fact much easier. You don't have to do all those calculations, because when you have a simply supported beam on two sides, or slab on two sides, then you know that this is 5. And when one side is fixed and the other one is simply supported, this number is 2. So if you remember those numbers, then you can immediately write this equation. Of course, for B, it's a similar equation. So we look now at the slab in the direction of B. We call a bending moment positive when the bottom fiber is in tension. So all bending moments like this, we call it positive, and the others, otherwise we call it negative. So in direction of A, we are looking, in the direction of B, we are looking to the positive bending moment in the middle of the span, which is of course given by the load times b squared over 8, plus that we know that the load QB was a function of Q, the total load, and the geometry of the slab. Those two together gives you the maximum positive bending moment in the direction of B. In direction of A, simply supported and fixed end support, we have on top here the negative bending moment MAN, N for negative. And on the bottom, we have the positive bending moment MAP. For MAP, we have this equation plus the one that we already got from QA, and it gives you this relationship. For MA negative, for this bending moment, then we know this bending moment is Q8 squared over 8. So plus the QA that we already have calculated gives you this expression. Now we got 3 expressions for the 3 different bending moments in our slab. Let's have a look now at the 3 different bending moments that we have found. Then you see that we have to calculate the total depth of the slab. And for that, we will use the maximum bending moment. When you look closely at those three formulas, then you will see easy between those two that this is smaller in bending moment than this, because all that is equal. This is all equal. It's only this coefficient. And then when you compare it with this bending moment, MBP, you see that this is a to the fourth, and a is much bigger than b, so this is most likely bigger than those two. So in order of scale, MBP is the biggest. So we'll concentrate us on MBB to determine the needed depth of the slab. First, we start with the load on the slab, which is the permanent load. But the permanent load depends on the proper weight of the slab, so that we don't know. So we put in H. H is expressed in millimeters, so that's why we have to divide by 1,000. This is the permanent load times 1.35, and the mobile load is 5 times 1.5. The bending moment, MBP, is then equal to 3.4 times Q. The optimum bending moment of the optimum depth, of the slab is now given by this expression. But pay attention, in the coefficient 97, there is already included the units of the different parameters. For instance, D in this formula is expressed in millimeter. The concrete quality, SDK, the characteristic value of the concrete quality is expressed in Newton per square millimeter, and the bending moment is expressed in kilonewton meter per meter. So only then you can use this formula. This is in kilonewton meter per meter, this is in megapascal, and then this will be in millimeters. We do not have yet the concrete cover or the position of the point of gravity of the tensile reinforcement. In our case, we are in an environmental class XC1. That means that the concrete cover is equal to 15 plus the maximum diameter of tensile reinforcement, which is 20 in our case, so C is 35. Now what we got is that the total depth of the slab is C plus V over 2 plus D. It means it's 45 plus D. Now it's easy. You fill in this D, you replace this D by this expression, you replace MBP by this expression, and you replace Q by this expression. Now you got only one equation in H, which is the total depth of the slab, and when you calculate this, you find H is 176 millimeters. Of course, we will go to round it off. We will use 180 millimeters, sorry, not 175, because 175 will not fulfill all requirements. So as from 176, those four expressions are okay. So we take H is 180 millimeters. We fill this in this expression, and we find the total load, which is 13.575 kilonewton per square meter. We calculate the bending moment, which is 3.4 times the total load. It's 46.14 kilonewton meter per meter. We calculate the other bending moments, and we check if this assumption was correct. So you see MBP is yes indeed bigger than MAN, and is bigger than MAP. So we are correct. This is correct. So H is 180 millimeters. Now we'll we'll now calculate the needed reinforcement. We know that the positive bending moment, which means at the bottom of the slab in the direction of B, which is this one, we have this as a bending moment. So there, in this direction, the first layer of reinforcement will be put. MAP, then this is the bottom reinforcement in the direction of A. And it's also, and this is put in the second layer, because this is put in the first layer, this is on top of it. And then we got the negative bending moment. So that's the bending moment at the top of the slab in direction of A. And we put that in the first layer on top. And of course, there is also a second layer on this side. In this top reinforcement in the direction of B is in fact 0, but we have to put always the minimum reinforcement. So don't forget that at least the minimum reinforcement must be there. So if the reinforcement to cover MAP is smaller than the minimum reinforcement, you will replace this by the minimum reinforcement.